This is Unit 1, the alphabet and grammar of geometry. Preview video 1.4, the logic of geometry. Finally got the music to work. First 3 videos, it wasn't working. So sit tall and ready. Here we go. Inhale. Hold your breath. Birthday candle 5. Do it again. Ready? Inhale. Hold for 3. Drop your shoulders. Ready? Inhale. Exhale. All right. Taking a look here. You're in your preview notes. You also even need your reference booklet today. So get your reference booklet handy. Don't forget date, time, and location, as well as a parent regarding the sign up. Here's your review page. You put your finger on the word draw, and you're going to read it out loud. Remember, we read with 3 body parts 3 times. So you read out loud, then you go back and filter, and then you go back and draw and cross out. And you're going to do this on your own. Pause the video. Okay, welcome back. You should have a red pen. And you are correcting the work. So you should have something already drawn. It's okay to be wrong. It's not okay to copy. Listen, if all you're doing is copying this page, Matt, you get the points, baby. But is it a learning experience? No, you learned to trace and copy when you were in kindergarten, 1st grade. Now's the time for you to use your brain. It's okay to be wrong and correct. It's not okay to copy. So right here, we have an obtuse larger angle, EFG. Obtuse means bigger than a corner. Obtuse. So we're going to do bigger than a corner. It does not matter which way this opens up or down or sideways. But it should be bigger than 90 degrees. EFG, F needs to be the hinge point. Does not matter which side is E or G. Drawn an interior ray, FH. So that F is the same as that F. There's another point we're going to add here inside, somewhere inside of this angle, so that EFH is the larger angle. So we're going to angle H slightly this direction, so that EFH is larger than HFG. All right, so what's important here is the fact that this is angled so that EFH is the larger angle and HFG is the smaller, and F is the vertex. If you have all those components, whether it's flipped the other direction, totally fine, start smiling. If you messed anything up, totally fine, correct it, and also write yourself a note. What do you want to remember? Lesson 1.4, the logic of geometry. Read these words out loud as I check them. You read, use your own mouth, out loud, read. Again, I'm mouthing the words because I want you to provide the sound. So English has 26 letters. The geometry alphabet consists of only 5 point, line goes on forever. Segment, piece of a line. Ray, half of a line going one direction. Plane, any two-dimensional space. That's it. Those are your 5 letters. You put them together, you get words. Your first word was the humble angle, which is 2 rays put together with a common endpoint. That was your first geometry word. Today, we're going to talk about the grammar of geometry, how geometry is put together using logic. Logically. Terms you're going to need today. Something called a conditional, which you are already an expert at. Converse, inverse, contrapositive, inductive reasoning, deductive reasoning. All of these are related to the logic or the grammar, how we put things together in geometry. You're going to need your reference booklet handy, so go grab that. You're going to need it later. Now, conditional. Conditional, you are already an expert on this. Great. You've heard this from parents, from teachers, anyone in authority, maybe even a friend. If you do this, then this happens. If you clean your room, then you may go to a movie with friends. If you do your homework, then you're more likely to do well on assessments. If you get a job, then you can make more money than your allowance. Whatever it is, if, then. That is called a conditional statement. If, then statement. It implies there's a cause and an effect. Now, you could have a cause and effect statement without the words denotating if then. I'll give you an example of that in just a moment. But a good example of something that doesn't have if then, but is cause and effect is commercials. So an example of things that don't have if then, that are cause and effect, are commercials. Entertainment ads or trailers, because what they're communicating is if you buy this product, if you go to this movie, then something good happens. You buy this product and you're healthier, you drive faster, you drive safer, you cook a great meal. If you go to this movie, you will find yourself laughing or crying. So all entertainment ads and commercial, whether it's on media or whether it's even written in a magazine or whatever, is it communicates a cause and effect. Here is a simple logo. Walmart, save money, live better. That's like their slogan. And what it's communicating is this, is if you shop at Walmart, then you will save money and live better. I would like you, in 10 seconds, you should be able to do this super quick. It's very obvious. I'd like you to spot what is the cause and what is the effect. Go. 10 seconds. Write it down. So the cause here is, of course, shopping at Walmart. Shop at Walmart. And what they're saying is, if you shop at Walmart, then you will save moolah and you will live better. That's the advertisement. All advertisements are essentially conditional. In any conditional statement, the cause is also called, fancy name, the hypothesis. And the effect is also called the conclusion. Now, all conditionals, cause and effect. Remember, conditional is simply cause and effect. Can be modified or switched around 3 additional ways. Okay, and right now I'm just going to give you the words and I'll explain them in just a moment. Converse means to switch the order. Inverse means to say the opposite or negate. I'm using hand signals. You're going to use them in class too. So inverse means to negate, which is a fancy way of say the opposite of. Opposite. Contrapositive, you switch and negate. Switch and negate. You do both. You need to have converse, inverse, contrapositive memorized. Let me give you an example. If it is sunny this weekend, then we will go to the beach. So if it is sunny would be the cause in this case. Then we will go to the beach. We will go to the beach. That is the effect. If it is sunny, we will go to then we will go to the beach. That's your cause and effect. This is your conditional, your original conditional. Put your hands up. Repeat after me. Say, if it is sunny, then we go to the beach. If it is sunny, then we go to the beach. That's your conditional. Ready? Converse switch. Converse switch. If we go to the beach, then it is sunny. Now, it doesn't mean logically whether or not this makes sense. You just need to know how to manipulate it. If we go to the beach, then it is sunny. That's converse. The original. If it is sunny, then we go to the beach. Follow along with the hands, please, okay? If it is sunny, then we go to beach. Inverse negate. So inverse flip, I call it, or say the opposite. If it is not sunny, then we won't go to the beach. That's inverse flip. If it is sunny, we go to the beach. Contrapositive, switch and flip. Flip. If we don't go to the beach, then it's not sunny. So converse switch, inverse flip, contrapositive switch and flip. Do that with me one time. I'm so serious. The more you get your hands involved and a rhythm involved, the more likely you're to memorize this, which you need to. Ready? Converse switch, inverse flip, contrapositive switch and flip. So let's write this out. Converse would be if we go, I'm going to shorten this up just a bit. If we go to the beach, so I'm going to botch the grammar here, but I want to just get to the very essentials. If we go to the beach, then it is sunny. Converse switch. Inverse flip. If it is not sunny this weekend, then we don't go to the beach. Again, I'm botching the grammar because I'm trying to keep it simplistic so you can see it. Inverse flip. Contrapositive switch and flip. If no beach, then ready. I want you to read this, and I want you to take that original conditional and write the converse, inverse, and contrapositive. Okay? Do this on your own. Welcome back. You should have a red pen handy, and I'm just going to type this out. So the original conditional is if you eat an apple, then you eat a fruit. Converse would be like so. If you eat a fruit, then you eat an apple. The inverse should read like this. If you don't eat an apple, then you didn't eat a fruit. I'm trying to be nicer with the grammar here. Inverse flip. Contrapositive, switch and flip. If you don't eat a fruit, then you didn't eat an apple. All right, star smiley, if you got all those correct, the basic premise. If you didn't get correct, I expect a little note. What do you want to remember? Okay, now we're going to talk about the truth value of a statement, the truth value. So our original conditional is if you eat an apple, then you eat a fruit. So if you're eating a piece of apple, then you've eaten a piece of fruit. And is that a true statement? And the answer is yes, of course, because an apple is a fruit. Let's do the converse switch. If you eat a fruit, then you eat an apple. Wait a minute. Really important you get this. If something is only sometimes true, you must mark false. In geometry logic, something is true only if it's always in every case true. If it's only sometimes true, sometimes not, you have to say the statement is false. Okay, for example, if you eat a fruit, then you eat an apple. No, you could be eating a banana. And if you eat a banana, that's not an apple. So that's a sometimes false statement. So you must make it false because it's only true if you're eating an apple. Ready? If you don't eat an apple, then you don't eat a fruit. That's the inverse. That's also only true if what you're putting in your mouth is an apple. Again, if you don't eat a different other item, then it could be a fruit other than an apple. So if it's only sometimes true, you must hit false. Last one. Last one is if you don't eat a fruit, then you don't eat an apple. So if you don't put a piece of fruit in your mouth, you cannot possibly have put a fruit, an apple in your mouth, and that is true. This leads you to one of our logic laws. And this logic law is called the law of contrapositive that says if the conditional is true, only the contrapositive is forced to also be true. The converse and inverse are like maybes, so we say it's false. If the conditional is true, only the contrapositive is forced to be true. Now, there is an exception or another rule that says when a statement's conditional and contrapositive, actually not contrapositive, converse, are both true, then the statement is called biconditional. And we will talk about biconditional statements in class. Most of geometry concepts are biconditional. So the law of contrapositive is one of your first logic laws. Here is another form of logic, inductive and deductive reasoning. Just take a look. I have several photos of golfers here, some famous. Take a close look. What piece of clothing does every single golfer have? Obviously, they have some sort of shirt. They have some sort of pants or shorts. But I mean, that's ubiquitous to everyone. But notice every single one of them is wearing a hat. Or you could say a visor, which makes sense because you don't want the sun in your eyes when you're trying to gauge distance of a ball. So let's say you went to every single PGA competition, dozens and dozens and dozens of golf matches. And you noticed every single player either has a visor on or a whole hat on, every single one of them. Okay. And then you come to the conclusion, let's say you knew nothing about professional golf attire. You decide to attend all professional matches for a year and observe. You observe hundreds of professional golfers, and you conclude that if someone is a professional golfer, he or she will always wear some form of hat on the course. You come to the general conclusion that all professional golfers wear hats on the course. This is an example of inductive reasoning. Write this with your hands. Say you take in observations and you have a truth, general truth moment. You take in the observation, hundreds of golfers seem to wear hats. Truth, general truth. Golfers wear hats on the course. That's inductive. Okay, so inductive reasoning means you have multiple observations or data points, and you come to a general truth. That's inductive. That's why I put my hands like this and you go in, aha, general truth. Deductive reasoning is you take the general truth and you apply it to a specific situation. So if you take your aha general truth and you apply it to something or someone specific, like you're pointing to someone specific, that's deductive. Ready? Go like this with your hands. Go like this. Go in. Aha. Truth. Inductive. Ready? Deductive. Aha. Truth. Specific. That is deductive. Let me show you how you can use this. Now, go back to our example. After multiple observations, you come to the conclusion that all professional golfers wear hats on the competition course. Now, let's say you meet a Mr. Tinvu at a restaurant. There's Mr. Tinvu. And he tells you he's a professional golfer. Now, right now, he's in some sort of suit. He's obviously not wearing a hat. He has a tie. He's sitting in a restaurant in a full suit and a tie. But what assumption can you make about his choice of clothing when he's on the golfing green? And the fact is, you would apply our deductive reasoning, our general truth. We would say, Mr. Wu wears a hat, even though at that moment you don't see him in the restaurant with a hat on. Deductive reasoning discovers truth. Excuse me, inductive reasoning. Inductive reasoning discovers truth. Deductive reasoning applies truth to a specific situation. Here's what you're going to do. You're going to read these out loud and determine whether it's inductive or deductive reasoning. Both of them. You can do this on your own. Out loud read now. Pause. Alrighty, students, welcome back. You have your red pen. Get ready to correct. Remember, you're not copying. Please don't copy. Do your own work when I say pause. Use your own brain cells. That's how you grow as an individual. So you should be correcting, not copying right now. Keywords here, you know Olympic athletes must win at a national level prior to international. Gabby competes. The fact that you start with the truth, okay, and you apply it to a specific situation, Gabby Douglas, that is deductive reasoning. You apply a truth. Okay, you're testing a hypothesis. All right, and you read all that, and there's conducting an experiment. This is a very, very famous experiment. And you determine that items fall at the same rate regardless of mass. You are taking in observation and data points, hundreds of experience. That is inductive reasoning. You discovered a truth, not applied a truth. You need to know the difference between inductive versus deductive reasoning. In geometry, most of the discovering of truths process or the inductive reasoning aspect of this math class has already been solidified over thousands of years of hundreds of mathematicians from around the world on every continent doing multiple math experiments, hands-on experiments, testing. So therefore, most of the truths that we are using in geometry have already been discovered. Therefore, most of the time we are using deductive reasoning. What are some of the famous people that did the heavy lifting for the inductive discovery of truth? Discover truth. In geometry, probably the most famous or infamous, depending on how you look at it, would be Pythagoras, around 500 BC, Plato, Euclid, you probably even heard the term Euclidean geometry, Hypatia, 400 AD, Brahmagupta, 600 AD, Khayyam, 1100 AD. These are just a small sampling of mathematicians from around the world who have discovered geometric truths that we will be utilizing and applying in this class. Now, before we go to geometric truths, we need to review algebra truth. So go to your reference booklet and find this page. If necessary, pause the video. Find this page. It says the logic of geometry. Now, even though it says geometry, it's a bunch of algebra. We're just going to zoom through a bunch of algebra truths that you already know. It's going to refresh your memory. So if you need to, pause the video and go find this page. Welcome back. Okay, very quickly, I'm going to go over right here these algebra truths. We're going to use these algebra truths to answer the why question. Why is it logical? Ready? Distributive property. circle, distribute. That's called distributive property. Add or subtract, addition, subtraction of real numbers. We're working on one side of the equal sign. You know this probably as collect-like terms. Adding, subtracting, ready, underline, add it together. That's called addition, subtraction of real numbers. You know this as collect-like terms, usually. Multiplication, division of real numbers. Again, you're working on only one side of an equal sign. So here's one side. So here, if you were to multiply these fractions, if you're working on one side you learned previously, you can cross cancel. Okay, on one side of an equal sign. So the 2 goes into 16 8 times. That's a 1. 5 goes into 15 3 times. 5 goes into 24 times. That reduction I just did is called multiplication, division of real numbers. Now, if you start adding and subtracting across the equal sign, that's called addition and subtraction property. That means you are now crossing the equal sign back and forth. Addition, subtraction property. It would look like this. I want to get rid of that 2. I add 2 both sides. That is called addition, subtraction property. Multiplication, division property. Again, you're working back and forth across the equal sign. If I were to solve here, 5 by 6. Okay, that's called division property. Taking a look here, cross multiplication property is when you have 2 fractions across an equal sign. Looks like this. You can multiply across the equal sign. You may not cancel across an equal sign. Notice I did not immediately distribute. Never cross multiply and distribute in the same step. That's 2 different steps. So that's called the cross multiplication property. Cross multiply, not cross cancel. Let me show you what I mean by cross canceling so that you know what's wrong. What I'm about to do is wrong. So don't follow, just watch. I'm going to do it in red pen so you can see it. See that 10 and that 8? If I do something like this, oh, 2 goes into both. 2 goes in there 4 times. 2 goes in there 5 times. That would be wrong. That's cross canceling. That would be wrong. Another thing that students commonly do, looking at this over here, is they cross cancel, and then they also have singles and couples mixing and mingle, which you can't. Singles and couples don't mix and mingle. They go like this. Oh, I got a 3 here and a 9 there. I can go like this. 3 goes in there 1 time, 3. What I just did there was wrong on 2 levels. I cross canceled across an equal sign, and I had a single and a couple mix and mingle. So what I just did in red was incorrect. Don't write it down, just observe. Square root property. To undo a square, use square root both sides. To undo a square, use square root both sides. To undo a square root, you square both sides. So the inverse of squaring is square rooting. The inverse of square rooting is squaring. On the right-hand side, I'm going to show you what is incorrect. X squared equals 64. I go like this. and I end up with x equals 32, that would be wrong. The opposite of squaring is not dividing by 2. The opposite of squaring is square rooting. The inverse operation of square rooting is squaring. 2 more, we'll be done. Substitution, super easy. If I have 3x equals and I say the definition of x is 8 and I want to evaluate the expression, you just substitute it in. That's called the substitution property. Properties with variables, if I have x plus x, that's 1x plus 1x, that's 2x. If I have x times x, that's not 2x. That is x squared. That should be in your reference booklet. And go ahead and summarize what are 3 main concepts that were new to you in this lesson.